Okay, now let's say you've got some great sources of information. How do you make sense of the actual research findings themselves? How can you tell if the evidence means what it appears to mean? Are the conclusions supported by the evidence? The following are some guidelines to live and die by as a scientist, so please take note. First, I cannot stress this enough. Just because two things both happened does not mean that one caused the other. Even if one thing happened directly before the other thing happened, you still can't count on correlation being causation. So tattoo this on your arm and review it often, because I will ask you often, does correlation equal causation? And you'll know that no, that is often not the case. When you read scientific articles that say they found a link or association or correlation between two things, that's great, that's all well and good, because it's a first step towards seeing if one causes the other. But unless it's an experimental study, and we'll talk more about that later, we cannot say that we know about causation. Now here is one of my favorite studies of all time, published in the New England Journal of Medicine, one of the most prestigious medical journals in the world. Now the main findings are shown in this graph here, where the x-axis is the per capita chocolate consumption, the y-axis is the number of Nobel laureates adjusted for the country's population. The trend clearly shows, if you look at it, that countries who consume more chocolate produce more Nobel laureates. And that's exactly what the authors jokingly concluded. So go spread the good word. Not only could chocolate improve your intelligence, it could improve the intelligence of our whole United States population. If only we ate more chocolate, we could catch up to Switzerland maybe in Nobel laureates. All right, what are the possibilities here? First possibility, maybe chocolate really does lead to more Nobel laureates. Possibility 2, maybe having Nobel laureates leads to chocolate consumption. Maybe every time somebody wins this award, the whole population celebrates by eating more chocolate. Or maybe there's a third possibility, something else, something that we haven't even talked about at all, leads to both more chocolate consumption and more Nobel laureates. Or there's even a possibility 4, maybe measuring chocolate consumption is actually the same thing as counting Nobel laureates. Like, for example, if countries are only allowed a quota of as much chocolate within their borders as directly proportional to the number of Nobel laureates they've won. Does that sound absurd? But is it really any more so than possibility number 1, where eating more chocolate leads to population-wide intelligence? Let's look at another example. This is a study that was not a prank or a joke like the previous one, but a real study. And you can read the title, No Booze? You May Lose. Why Drinkers Earn More Money Than Non-Drinkers. And basically, in this study, they found that people who report that they drink alcohol, compared to people who abstain from drinking alcohol, earn more at their jobs. And they concluded that social drinking leads to more social networking and leads to better jobs, leads to higher earnings. But is it really drinking that causes higher earnings? What if people with higher earnings just have more disposable income to spend on alcohol, especially expensive alcohol served at bars? And also, if it's really the social networking that comes with the drinking that is supposed to lead to more income, then how come non-social drinkers also earn more money than abstainers, as found by this study? I'll let you chew on that one yourself. So remember, the only way to know that it's causation and not just correlation is through experimentation. Manipulation of the independent variable, that's the key to what experimentation means. You actually have to change the independent variable. In our chocolate example case, that's the chocolate consumption. And then we measure the change in the dependent variable. For example, the IQ of the population or the number of Nobel laureates. So, for example, an experimental study might look like this. We measured at baseline IQ in 100 adults. Then we randomly assigned half of the participants to the chocolate group and the other to the no chocolate group. After 6 months of feeding 10 grams of chocolate per day to the first group and restricting access at all to chocolate in the second group, we again measured all participants' IQ. And if after all that, and the authors made sure to control for confounding variables, like making sure that one group wasn't predominantly more educated than the other group, and the gender balance was roughly equal, and socioeconomic status was roughly equal between the groups, basically ruling out the possibility that something other than chocolate consumption could have differed between the groups. Then I'll believe it. The other very important guideline for evaluating research is to pay attention to effect size and significance. So specifically, we'll have to look carefully at graphs and read the fine print in results. And here's what I mean. Often, titles and headlines related to scientific findings will say X significantly predicts Y, or there is a statistically significant relationship between X and Y. But what does that mean exactly? So in scientific language, statistical significance does not refer to magnitude or importance. It refers to confidence. So for example, if you see a sentence that says, the amount of chocolate consumed significantly predicted IQ, and in parentheses, p less than 0.05, that actually translates to, there is a less than 5% chance that the chocolate IQ link we found was a complete fluke. Or in other words, there is a more than 95% chance that the chocolate IQ link we found is a real effect. So let me just clarify that again. So when you see that there is a statistically significant relationship between X and Y, and the p-value is less than 0.05, that means that the relationship found between X and Y is most likely not a fluke. In fact, we're 95% confident that it is not a fluke. So why 95% confidence? Why is that the accepted confidence cutoff? Why do we publish findings that have a 5% chance of being false, but not 6%? Well, it turns out there's actually no magic about 5%. This is just the convention that scientists and statisticians decide to agree on. It's not a perfect system, and that's why in just a moment we'll talk about also looking at effect size and not just effect significance. But for now, it's really important to know the convention of statistical significance and the p less than 0.05 cutoff. So when you're reading about significance, be aware of a few things. So first of all, be aware of trusting findings that are not statistically significant. So for example, if you read something like, income is positively correlated with self-reported happiness, p equals 0.27, well, this actually means that there is a 27% chance that this finding was a total fluke. And maybe for some things, a 27% chance of it being a fluke is okay, but in science, we really can't trust something like that. We also have to be aware of dismissing findings that are not statistically significant. For example, if you instead read something like, income is positively correlated with self-reported happiness, p equals 0.07, this means that there is only a 7% chance that this finding was a total fluke. Now, this is not ideal. 7% is not a trivial amount of risk. But just because this is 2% too risky to be called statistically significant doesn't mean it's a definitely false finding. In fact, by definition, it is still highly likely to be true, most likely true. You'll just have to sort of judge for yourself whether this is an acceptable level of risk for having a fluke finding. Lastly, we also have to be aware of ignoring how many times the scientists try to reach 95% confidence. So on this point, I think a comic strip actually does a better job explaining this than I could, so please go to the link provided in Module 3.2 in Bridges right underneath this video and read the comic and its explanation. I will also post a participation forum in this module that will be on this comic and about it, where you can earn your participation points for this module. Now let's talk about effect size. In scientific language, effect size refers to exactly what it sounds like, how big an effect is. So for example, if you saw something like, participants in the chocolate group improved their IQs significantly more than participants in the no chocolate group, and in parentheses you see p less than 0.05, which we already know what that means, and then Cohen's d equals 0.04. Now that translates to, we're very confident that participants in the chocolate group improve their IQs more than those in the no chocolate group, but only by a tiny bit. So let's talk about why that is. What you need to be aware of is how big the effect is, practically speaking. So don't just be satisfied with statistically significant, because remember, that does not necessarily mean that the effect was of a significant size. So it's better to understand, or even better than that, mentally picture the size of the effect, if possible. So let's talk about another example. If you were looking at a clinical trial for a weight loss drug that was found to significantly reduce body weight, remember here again that significantly doesn't mean people lost a significant amount of weight. It just means that statistically, there is less than 5% chance that whatever the finding is, it's a fluke. Make sure to check out the effect size of the findings. So did people lose 2 to 3 pounds over the course of 6 months? Or did they lose 20 pounds in 2 weeks? That's a huge difference, right? So here, effect size would give you a better sense of just exactly what the researchers found. So conventionally speaking, an effect size of 0.2 is considered small, 0.5 is considered medium, and 0.8 is considered large. Of course, that does not necessarily apply to all statistical analyses, but we'll talk in more detail about each of the different ones in future modules. For now, it's pretty safe to go by those conventional standards, and if you're reading a research paper, the author should have also described in words how big their effect size was. So be sure to read the fine print in the results section. Next, we also have to be aware of misleading graphs that make effects look bigger than they actually are. So here's what I mean. Look at this graph on the left here. So on the x-axis, we have the year, 1998, 1999. On the y-axis, we have the average house price. And on the bottom here, we have 80,000, and then going up 81,000, 82,000. And the headline is massive increase in house prices this year. Because, I mean, look at it. The bar for 1999 is way bigger than the bar in 1998, right? There's such a huge increase in house prices. And it even looks like house prices more than doubled. But then if you look again at the y-axis, you notice that the price increase really just went from 80,000 to 82,000. And while 2,000 is a lot of money, it's a drop in the bucket given that we're talking about $80,000 houses. On the other hand, if you do a proper graph by zooming out and start the y-axis from 0 like an honest scientist, you'll see that there is barely any difference at all between 1998 and 1999. So always know what you're looking at before you believe it. So to summarize and review modules 3.1 and 3.2, where and how you find your information is important. And then when you have your information in hand, it's important to evaluate just what it means instead of blindly trusting the titles and headlines. Specifically, we want to be looking for information from reputable sources, starting with an agnostic attitude. Number two, we want to ask ourselves the 5 W's about the source of the information: the who, what, when, where, and why. Third, we always want to remember that correlation does not mean causation. And four, size matters, and so does statistical significance. There are many more rules, guidelines, and tips for how to critique research and, in turn, prevent yourself from designing research poorly yourself, and we will be learning those as we go along the semester. But the ones that we learn here today, I will call absolutely essential to remember. So you can always default back to these. And in your annotated bibliography, which is assignment 2, I'll be looking specifically for your evaluation of the studies that you found using these concepts, especially concepts number 3 and 4. So, for example, if you found a study by Smith published in 2011 that showed that TV watching is linked to depression in children, I want you to explicitly say if this is true, but this study only showed correlation, not causation, because the authors did not experimentally manipulate the amount of TV watching. So A+, if you are able to evaluate each of the studies that you found and point out limitations, point out future directions, point out things that are missing, or you can even phrase it as something that you can do better in your study, and that would actually be ideal. So on that note, let's take a break, and when we come back, we'll do a demo of, practically speaking, how do you go about looking for study articles.